Welcome to lesson 2 of unit G482 module 1 electric current, and today we're going to learn about the electron drift velocity. The first objective you need to be able to do is to define the electron drift velocity and the number density. You also need to be able to explain the difference between speed of an electron and the electron drift velocity. You need to be able to perform calculations involving the electron drift velocity equation. And you need to be able to compare and explain the conductivity of metals, insulators and semiconductors. First of all, I'm going to show you a short video which hopefully will help you understand what this term electron drift velocity is and what the difference between the speed of an electron is and electron drift velocity.
An electric current results when charged particles move in one direction. The blue dots represent the charge carriers, of which electrons are the most common. In metals there are very large numbers of electrons which move easily. Due to the thermal energy of the metal, they dance and vibrate rapidly, in all directions. Let's extend this bit of wire, but concentrate only on the electrons we saw in the first place. If we apply a potential difference to the ends of the wires, the electrons will still vibrate randomly, but at the same time they will drift in one direction. It is this drift which is an electric current, and the average speed with which the electrons drift is called the drift velocity.
Okay, so you've just seen in the last small video that there's a difference between the speed of the electrons and their average velocity in a certain direction. This average velocity in a certain direction is what we call the electron drift velocity. It should be clear to you that there is a link between this electron drift velocity and the current that is flowing through a wire. So let's see if we can come up with an equation for it that links the two together. So let's consider this wire with a current running through it, and we're going to consider this small part zoomed in this cylinder here. Now we've got our delocalized electrons, our conduction electrons, and we've got n of them per meter cubed. This is the number density, and it is a definition you need to know for your exams. It is the number of free conduction electrons per meter cubed, and they're all traveling at an electron drift velocity of v overall in that direction. And this electron drift velocity is another definition you need to know. It is the average velocity of an electron as it travels through a wire due to a potential difference. So we are going to try and come up with an equation that links the current through the wire and the electron drift velocity, but it's also going to link in number density. So remember the equation we gave you before. Current can be found by dividing the amount of charge that flows past a point in time t divided by the time it takes to go past that point, t. Let's consider that point to be the surface of the cylinder, this end. So Q will be the amount of charge that flows past that point in time t. Now we can work out the number of electrons that flow past that point in time t as follows. The electrons will reach the face of this cylinder, and after a time t they will have travelled the whole length of this cylinder. Now if a time t elapses as we go from there to there, and if they're travelling at speed v, that means that distance will be v times t, from the equation of distance equals speed times time. Now also, the surface of this cylinder has an area of a meters squared. So therefore the volume of this cylinder will be a times v times t, because it's area times the length of the cylinder. That means that the volume of electrons that go past the point in time t equals a v t. Now don't forget, we've got n electrons per meter cubed, and if this is the number of meters cubed we've got, then that means the number of electrons that go past the point, and remember this is the point in time t, is equal to the number of electrons in that volume, which is equal to the number of electrons multiplied by the volume, NaVT. Now, don't forget that each electron has a charge of E. So therefore, if this is the number of electrons we've got, then the total charge we've got that goes past this point in time t is equal to NaVT multiplied by E. Now, don't forget, current is defined as the charge that goes past a point per second. So to do that, we need to do to work like that, we need to do charge, which is this bit here, divided by the time. Now, the time which has elapsed is just t. So if we divide all of this by t, the t cancels out and we're left with NaVe. And that is our equation that links current to number density and electron drift velocity. Current is equal to the number density of a metal multiplied by the area, the cross-sectional area of the wire, multiplied by the electron drift velocity multiplied by the charge on an electron.
Okay, let's use this equation now and see how we could if we can see how the number density affects the conductivity of different materials. So we're going to look at different materials, we're going to look at their conductivity and see how that is controlled by the number density. So let's start off with two materials we know about, metals and insulators. We know that metals are really good conductors of electricity, and so therefore they have a high conductivity. That means they can allow big currents through them. Insulators, we know they're not good conductors, so they have a low conductivity. So that means the current they allow through them is really low. So if we want to compare metals and see how the number density, if we want to compare metals and insulators and see how number density controls the conductivity, then what we need to do is compare like for like. That means we need to compare a metal and an insulator that have the same cross-sectional area and the same electron drift velocity. And obviously they're going to have the same charge on each electron because that's a constant. So if we're assuming both for metals and for insulators that A, V and E the same, then for metals I can be high only if N is high. And that means the number density must be high. Likewise, for insulators, if the conductivity is low, that means the current is low, and therefore we must have a low number density, a low number of electrons per meter cubed. And then we've got these new materials that you don't need to know much about, called semiconductors, but what you do need to know is that their conductivity is medium, somewhere in between metals high conductivity and insulators low conductivity. In fact, the conductivity of semiconductors ranges quite a lot, and as you guessed it, it depends upon the number density of the electrons in the material. And so we in fact end up with a number density in between a metal's high number density and an insulator's low number density. So there we have it. Metals have a high conductivity because they have a high number of electrons per meter cubed. Semiconductors have a medium conductivity because they have a medium number of electrons per meter cubed. And insulators have a low conductivity because they have a low number density per meters cubed.